Good morning. Thank you so much for invitation. So my title is Deep Learning and Computed Tomography. First of all, I would like to acknowledge my sponsors, including General Electric and Corning. Also, I would say what I'm going to present covers a lot of work jointly performed by my group and my collaborators. First, let's say something about general background. So I recently did a Google trend search. And if you see the popularity of the phrase artificial intelligence, deep learning, medical imaging, so this is what you see. And one interesting observation, and around the early 2016, we see deep learning artificial intelligence become very popular. And mainly deep learning as a mainstream of artificial intelligence attracted a lot of attention. And at this time point, and we wrote a perspective article on deep imaging, and we envision a direction from tomographic raw data to reconstructed image. This is in contrast to popular applications of deep learning from image domain to feature domain. And we organized the first IEEE transaction medical imaging special issue, got a lot of citation. Recently, we are organizing the second TMI special issue. And by now, we received the total number of submissions, 68, which is roughly twice as many as that we received for the first special issue. Evidence very strong. The field is still enjoy a strong momentum. Last year, we published the first book on deep tomographic imaging, so in collaboration with my co-authors, Professor Yi Zhang and Xiaojing Ye and Xuanqin Mu. Very soon, we have a review article to appear in Nature Machine Intelligence, and we gave a broad overview of this tomographic deep imaging field. So a lot of papers cited there. And several days ago, I accepted the offer to serve as a book series editor for IOP publishing. So we are going to organize a series of books under the common theme, artificial intelligence in biomedical sciences. So those of you who are interested in writing or editing a book, please feel free to contact me. So this is the outline for today's presentation. And basically, we say we will talk about the intersection of deep learning and computed tomography. And I will talk two aspects of this intersection. But first, from deep learning to CT, and we cover successful applications of deep learning in this field. Second part, and also in the intersection, but we talk about a few topics where CT projects waiting for successes of deep learning. Talk about first part, how deep learning techniques could be adapted or developed so that CT problem can be solved. We talk about 3-point and reconstruction, poly to mono, and the instability issue. We know the deep tomographic imaging field started a few years ago, and I would say the initial project is about low-dose CT reconstruction, how we can use deep learning techniques and to develop algorithms so that image noise can be successfully suppressed. And to my best knowledge, these two are earliest journal papers and received a good amount of citations. That shows deep learning pros can effectively remove image noise. And also we wrote a paper and we performed a high-level comparison. And we show modularized adaptive processing network. As shown here, we have multiple identical network modules. So we do processing progressively. And we bring radiologists in the loop. We compare deep learning results with commercial iterative reconstruction from major vendors. And a double-blind study show deep learning method could be comparable or superior to commercial iterative denoising reconstruction. And the GE Global Research Center and Healthcare also work in this domain. And several years ago, they got FDA approval to do deep learning-based image denoising. So this kind of image denoising is still image domain post-processing. And how do we go from sinogram domain to reconstructed image? And there are a number of good papers. For example, the paper from Sichuan University and also in collaboration with my group, and we have this unrolled deep learning network. So basically, we have multiple stages, and we can use deep learning to train each of them. And in each stage, and we have the traditional iterative reconstruction incorporated. And in parallel to that, you have a trainable imaging chain. And as a result, we could receive very good results for sparse view and field view limited data reconstruction. And to do the end-to-end training and mapping tomographic data to images is a very hot topic. Like in this Nature paper, and we could use case-based data as input, and just get MRI reconstructed image. A problem is about computational efficiency. So the data is reshaped to one-dimensional vector, and each point is connected to every pixel in the image domain. So the computational complexity is up to n to the power 4. N is the number of pixels along one side. Okay. The improvement was made by Guanhong Chen's group, and they perform end-to-end mapping and direct mapping from raw data to reconstructed domain. And they performed network design based on each and every projection profile, so that the fully connected network is built based on projection. And as a result, the computational complexity is reduced. So this is on the order of n to the power 3. And we did some similar design, but we try to do network connection based on individual datum and just link the datum to every pixel along the X-ray path instead of the whole field of view. So we call our network deep efficient end-to-end reconstruction called DEAR. In collaboration with Corning, we show and with DEAR and just 75 views, we can get a good denoising results in comparison to the ground truth. And from 300 views, the image quality seems very comparable. So this is direct reconstruction results. And another interesting study, we started 2017, and we talk about monochromatic CT reconstruction from current integrating data via deep learning. The idea is not that complicated. So you have a monochromatic X-ray spectrum, and you use current integrating detector. You got an image subject to beam hardening artifacts. Even you use some correction method, so numerical accuracy is still not perfect. On the other hand, with zero energy CT scanning, you could do virtual monochromatic imaging. So you have a gold standard, which is acquired with more expensive zero energy CT scanner. So if you have a current integrating scan with a single X-ray spectrum dataset, you can reconstruct this image. And on the other hand, you have a zero energy CT counterpart, and which give you virtually monochromatic results. You can do machine learning, okay? So bring the imperfect image, less accurate image to virtual monochromatic imaging acquired with zero energy CT. This is a method, and we implemented that method. There are several similar papers in this domain. On the other hand, we could do this. So this is an imperfect image. You can just use retracing, get a sinogram, and along each line, and I mean for each viewing angle, you got a projection profile. So because this is not accurate, this projection profile is not accurate either. And for polychromatic Beer's law, and you couldn't do line integral processing accurately. So this is not perfect. This is gold standard, so you got a perfect profile. We see the opportunity to do machine learning from this projection profile, not so accurate, to the accurate one. So you do this way. You see the input is a one-dimensional projection profile. And then we use 5 hidden layer and to do deep learning, and much simpler than what we could do in the image domain. And we get very reliable results. So this is a example. So you see with machine learning, we do zero energy monochromatic imaging. Then we go ahead and do material decomposition. So we got 3 material components: adipose, muscle, and bone. So the results are in great agreement with zero energy CT counterpart, and we can identify bone calcification. The overall relative error with deep learning method is less than 2%. So the paper published in patent recently. Okay, so this is interesting deep learning application. A very important thing I would like to mention. Early last year, National Academy of Sciences organized a symposium talking about the science of deep learning. After that, a special issue of PNAS was published, including about 10 papers. So this is one interesting paper talking about unreasonable effectiveness of deep learning in artificial intelligence. So we all know remarkable success in various fields. And very relevantly, another paper in the special issue talking about a problem with deep tomographic reconstruction entitled On Instability of Deep Learning in Image Reconstruction and the Potential Cost of AI. So in this paper, the authors reported 3 kinds of instability with several popular deep learning networks, including AutoMap. So the idea under their study is that they use so-called adversarial attack, small perturbation, and show network is not stable. So visually you see this is image. Network can easily clarify as a mounting. You add very weak noise and to the input, and you get this output. And for human, visually you see no difference, but a neural network will judge this as a dog with a high confidence level. So this is a problem showing network is not stable. Certainly a huge problem. So the 3 instability identified in the PNAS paper just mentioned. So summarized here. So strong artifacts from a tiny bit perturbation, the first type of instability, and some small subtle features go undetected, second type of instability. Last one, and you train neural network with a small amount of input data. And later on, after training, you give the network more input data. More data, supposedly you have more information, but the trained neural network show decreased performance. So the three kind of artifacts. The first kind of two artifacts are kind of familiar. So that is well known type 1 error, type 2 error. So this first one is nothing but a false positive. Second one is false negative. And if our deep reconstruction field got this problem, how could we trust deep learning networks will perform good health care? So that's a major challenge. And last week, we show a paper appear in Nature Machine Intelligence. That's a perspective paper. It gave a high-level understanding why we got all these problems. And they believe shortcut learning is the issue. They gave a very interesting toy example. So you have a training data set. You give a bunch of images, represent stars, and some images representing moon. And you train neural network, and the neural network can perform well if you just use training data set or similar data set. But if you give input data, something like this, and the network will perform poorly. But to human eyes, all this just very clear, either stars or moon. So why neural network got tricked here? And actually, you give further consideration to the example. You show all these training data set, put stars either bottom left or top right, and put moon either bottom right, or just the top left. So just things like this. And we can easily design neural network to classify objects according to their locations. So this is a good example of shortcut learning. So in this case, given the example here, and we can just use a single neuron and use a XO operation and to make a perfect judgment. But this is really shortcut learning. You didn't learn object shape, which is intrinsic feature. And we did some work and extend definition of artificial neuron from linear neurons. You got inner product, then subject to nonlinear activation. So we elevate this data summary part to quadratic function. Then a single quadratic neuron can do the XOR logic operation easily. So for the example I just mentioned, a single quadratic neuron will do the trick. So that gave us a hint. If network architecture is too simple, that would facilitate shortcut learning. If the training data set is not diverse enough, then that will lead to shortcut learning or overfitting. In the Nature Perspective article, and they emphasize the importance of OOD generalization. So IID data is independent identical distribution. OOD data, they mean data from significantly different distribution out of distribution. And to make sure machine learning does what we want the network to do, and we can just follow their advice to use a lot of good data, and particularly OOD data set. So data set 1, 2, 3, then the intersection will be likely our solution. So to help us remember, think OOD in different way. O means offset. So the data set the testing data set, OOD data set, should from a distribution that has a significant shift relative to your IID training data set. Second O is OK, means the OOD data set should have a solution. You cannot say I get OOD data significantly different, but they all random noisy background, and you have no solution in the new training data set. That's not good. And the difficulty means you give network a new testing data set. The data set should be quite challenging. You cannot just present a quite different data set, but easily solvable. So this will help us understand how we can make sure network will perform well. But what about instability issue? If you have all the OOD testing data, will you remove the instability problems I just mentioned and pointed out by the PNAS paper? We have a general answer. And in the perspective on deep imaging paper, the figure 5. So we say deep learning method can be used in combination with traditional iterative algorithm in many ways. So you can combine classic methods like iterative compressed sensing with deep learning in various ways. So all the algorithmic ingredients can be synergized together. This is general answer. And several months ago, we posted an article specifically address the PNAS paper. And we say we can use our well-designed synergistic network and with compressed sensing and iterative reconstruction components, and use the same data set, same algorithm they studied, we reproduced their instability. Then we use our network and to remove all the problem. So we call our network ISID network, and certainly you can implement the framework in different variants. A means analytic, C means compressed sensing, I iterative, and D means deep learning. So this is our first embodiment. So you have deep learning, get initial guess, you have compressed sensing to acquire certain level of kernel awareness, and you check residue via analytic mapping. You do so iteratively, then you get very good performance. So let me just show you what we got. The first type instability is new artifacts generated by neural network. First type 1 error, or called false positive. You see, this is the first type of instability. Second one is false negative. So pay attention, see the red arrow. So the artifacts generated by this deep neural network selected by the PNAS paper, you see these things problem. These artifacts not in the ground truth. The second part of artifacts or second type of instability, false negative. You see the green arrow. Originally, you see clearly the wing of the birds and disappeared. Okay, then PNAS paper, authors put, can you see it as a small feature through deep reconstruction and diagram, and these features gone. So these are instability identified by PNAS paper. With compressed sensing, the authors say compressed sensing has kernel awareness. So you have more stable results. You can see the letter, and you see the birds very clearly. And with our ISID network, because we synergize deep learning here and compressed sensing components into ISID, so you see our results do not suffer these two types of artifacts. The third type of instability, talking about when you get more data, network performance could be decreased. So if you trace this right curve, So you got a dip, you got a peak. All these indicate performance optimized at this point where the network got trained. So you got a better result. But when you give network more input data, you see network performance in terms of peak signal noise ratio, in terms of similarity, structural similarity, the performance gets decreased. And on the other hand, this purple curve is for our eyesight network, and we have the performance consistent to our intuition. More data, you get better performance. More data helpful. That shows we can systematically address the challenges posed by the PNS paper. And last month, we show article posted on archive from a totally independent group in Europe. They basically reported a similar thing, and with iterative deep learning and just combined together, network can be very stable. So this is the first part of my presentation. Second part, talk about something we are interested, and in the deep learning field, we can try to address this new problem, including interior tomography and photon counting or photon sensing CT and robotic CT scanning. So I will finish this part a little bit quickly. And the interior tomography, and those you are in CT field know data got truncated both sides. And traditionally, we know, and this is interior problem does not admit unique solution. And this is a classic textbook. So we can find very detailed, rigorous analysis from interior data set, and the ghost functions can be in the field of view, and the variation of the ghost is small, well inside ROI, but it increases rapidly towards the boundary of the ROI. So this is not a trivial problem. And our group and the collaborators and the peers revisited the problem since 2007. So we introduced a tiny bit of prior knowledge, a known subregion inside the ROI, and later on we use compressed sensing. We assume ROI is piecewise polynomial. And under these weak constraints, we show interior tomography is feasible, so we can perform accurate and stable reconstruction. And based on interior tomography, we designed a multi-source interior tomographic system for high-speed imaging. Interestingly, I show this year's RSNA meeting, a Chinese company proposed this multi-source design for ultra-fast cardiovascular imaging. This is a good problem for deep learning, so interior tomography with polychromatic data. So we are working along this direction using classic and deep learning method. Okay. Second part is photon counting detector. So you know photon counting allows you to record raw data in multiple energy beams. And the photon counting with cadmium telluride detector subject to strong charge sharing and pile up artifacts. So we have this whole workflow based on Ken Takuki's simulator. So we added some further functions so we can simulate the whole imaging chain. Strong artifacts can be corrected using deep neural network. So we got some quantitative results. So we are happy with this machine learning capability. And the next stage, we are collaborating with Mars in New Zealand with real photon counting detector data, and try to do quantitative photon counting reconstruction. And in parallel to this line of research with cadmium telluride detector, and we also work on deep silicon edge-on technology. Coincidentally, we show GE's announcement, and they acquired a photon counting company, Prismatic, and they use also deep silicon eyes-on technology. So 2 papers we published, the first author majority work by Zai Feng Si with Tianjin University. So these are 2 papers we wrote together. Zai Feng's paper, this one published 2016, and the recent one published last year. So the idea is use deep silicon, and we believe this is good technology. And in this figure, you see the working principle of CCD detector. You see this very nice animation shows that charge transfer can be driven by alternating voltage on electrode. So the CCD camera is well known. So this is CCD camera working principle. You got light signal vertically, but the deep silicon technology, and you got X-ray beam and penetrate the silicon substrate horizontally. So for conventional CCD camera, each time you read out one datum, but for this deep silicon technology, you read many data points. So the X-ray beam will be attenuated along the path, and depending on X-ray energy, you got different relative absorption. It's the first layer, second layer, third layer. So the relative absorption coefficients are different. Therefore, you can solve linear equations so that you can get energy sensitive information. We call this photon sensing mode, and it can be treated as an inverse problem. This can be also solved using deep learning. Last thing mentioned, clinical micro CT concept. We had a paper published decades ago, just try to get a very high clinical resolution in vivo, particularly for cochlear implantation. Recently, we are in collaboration with a European company called RD, and they got a robotic arm. So we try to use photon-counting detector to have material decomposition capability. And we have interior tomography deep learning, try to resolve subtle details in temporal bone. So this is something we are actively working on. Also a good topic for interior tomography and deep learning for high accurate geometrical calibration. Thank you very much. So this is a summary of my talk, a few points: reconstruction, virtual monochromatic imaging. This is the highlight instability issue in deep tomographic reconstruction. Interior tomography, photon counting versus photon sensing. I personally think photon sensing is a better way than photon counting. That's my own opinion in robotic scanning. Thank you so much.